Now let's look at finding a volume of revolution using shells. And this time we'll look at a situation where the area that we are revolving does not extend all the way down to the axis. So this is an area that's trapped between two curves. In this case, we're going to look at the region enclosed by y equal x and y equal x squared. And we're revolving that around the y-axis. So there's our region. I've drawn in the mirror image there to give me a sense of what that object would be revolved around. Now, we've looked at two methods, cross-sectional slices and cylindrical shells. If we were going to do cross-sectional slices, those disks would be stacked up the y-axis because we're revolving this way. So if we were going to do cross-sectional slices, it'd have to be an integral with respect to y. And these functions are given as functions of x. Y equals a function of x, y equals a function of x. So if we were going to do cross-sectional slices, we would have to invert these, rewrite these, solve for x, solve for x. Now in this case, those functions are simple enough that we could do that. We could write x equal y for that one, and x equals square root of y for the other, and we could do cross-sectional slices. But they are already given to us in terms of x, and as I mentioned before, depending on the functions, you may not have the option of being able to invert the equation. So let's stick with it the way it is and do our shells method. So first of all, we would partition that region along the x-axis, right? Remember, the underlying geometry is there's a bunch of rectangles vertically approximating that area, and then those rectangles are going around creating the shells. And all I want to do is draw one cylinder in order to figure out the geometry there and figure out the area of it. So if I just pick some random x location, create my cylinder by revolving around here. Now all I have to do is figure out when I clip that thing and roll it out flat, what is the area of that rectangle? Well, as always, this dimension is the circumference of that circle. Circumference is 2 pi r. The radius, this distance, is x. So again, that's just 2 pi x. But now this dimension, the height of this rectangle, is the height of that cylinder, and it's the difference between those two curves, right? That height is being determined by the distance between that top curve and that bottom curve. So bigger minus smaller, the bigger one is y equal x. The smaller one is y equal x squared. So this height, difference in the curves, bigger minus smaller. So the area here of this rectangle is that 2 pi x times the height, base times height. And now all we have to do is integrate up that area. So in order to do that, look at our partition. Now, from the picture, it's pretty clear that it starts here at 0. But we need to figure out what this x value is here where that region ends. We weren't given limits on x. We're just told that it's the region enclosed. So we have to figure out what is that intersection point. So we'll have to do that first. So we want to know when is x equal to x squared, or solving, gather everything to one side and factor. Set those factors equal to 0, and we get two solutions. So we found the obvious one, that they do intersect there at the origin, and they intersect there at x equal 1. So our volume, integral from 0 to 1, that's the interval of x that we partitioned, and we're just integrating up this area. Again, you'll always have that 2 pi in there. That just comes from the geometry of what we're creating. That circumference is always going to generate a 2 pi. So again, your first step would be to just get that constant out of there. Distribute your x through. And in that point, you've got a fairly straightforward integral, just a polynomial. That's just power rule. So again, a little bit different region here. This height isn't just a single function, it's the difference between two functions. So this will happen when the region that we're revolving is not right up against the x-axis. What we can look at next would be taking a region and revolving it about the x-axis. So let's think about that. With shells, when we run around the y-axis, that ends up generating an integral with respect to x. So when we go around the x-axis, we're going to end up generating an integral with respect to y. So those cylinders will be sitting on their side, and we'll be integrating up vertically with respect to y. So we'll look at that one next time.